In today's session, I will be discussing about interplanetary navigation systems. Interplanetary spaceflight or interplanetary travel, that is to travel from one planet to another planet, it can be a crewed or uncrewed mission between stars, planets, usually within a single planetary system. What do you mean by planetary system? It is a set of gravitationally bound non-stellar objects in or out of orbit around a star or a star system. Generally speaking, system with one or more planets constitute a planetary system. Although such systems can contain orbital bodies such as dwarf planets, asteroids, natural satellites and meteoroids. Example, solar system is a planetary system. All these 8 planets are revolving around the star called as Sun. And these planets will have their own natural satellites, and there is an asteroid belt within the or in between the planets. Spaceflight are confined to travel between the planets of a solar system. At present, there are several spacecrafts which en route or orbiting or preparing to land on other bodies of the solar system. There are spacecraft due to flyby and orbit asteroid and comets, and still other dedicated to monitoring the Sun and its impacts on rest of the solar system. Now if you observe the space, or if you just observe the solar system, we have n number of artificial satellites or man-made satellites, and there are spacecrafts which are traveling towards an orbit or towards a comet or to study their atmosphere, and there are few dedicated satellites to monitor the atmosphere of the Sun and to study the impact of the Sun radiation on the planets. The success of these missions and the amount and accuracy of these scientific data returned will depend on many other things. Example, how well the position of the spacecraft is known throughout its mission. So if you want to say the data obtained from particular satellite which was revolving the planet Mars, how you are going to say how it is accurate? Because if you are sure about the spacecraft orientation throughout its mission, you can say okay, it was in the desired orbit. So you can say that accuracy is okay or accuracy is high. You can relay this data, you can depend on this data for scientific investigations. This position determination is primary objective of interplanetary navigation. So the main objective or the primary objective for interplanetary navigation is to determine the position of the spacecraft or the satellite throughout the mission. What are the reasons for interplanetary travel? The cost and risk of interplanetary travel receive a lot of publicity. Nowadays, there is lot of publicity for interplanetary travels. Spectacular examples include the malfunctions or complete failures of probes with a crew such as Mars 96 Deep Space Mission 2, Beagle 2, and there are non-crewed missions which are successful, that is MOM or Mangalyaan and MAVEN are the few examples for interplanetary navigation or interplanetary systems. Many astronomers, geologists and biologists believe that the exploration of solar system provides knowledge that could not be gained by observing the Earth surface from the space. But at the same time they disagree about the whether human crewed mission make a useful scientific contribution. Some think robotic probes are cheaper and safer, while others argue that either astronaut advised by Earth-based scientists or Spacefaring scientists, advised by Earth-based scientists, can respond more flexibly and intelligently to new or unexpected features of the region which they are exploring. For example, other than a scientific probe, okay, consider both. If you are considering a scientific probe, it will react to the atmosphere or any unexpected features in a programmed manner. It should be programmed for everything. But whereas if you are the crewed missions, if you are sending humans or astronauts, they will respond in an intelligent manner and they are more flexible compared to the artificial probes. Many science fiction stories feature detailed descriptions of how people could extract minerals from asteroids and energy from sources including orbital solar panels, which are very strong magnetic field of Jupiter. Some point out that techniques may be the only way to provide raising standards of living without being stopped by pollution or by depletion of earth sources. So some people, they are telling like, instead of living on the earth, we should form a place or colonies on other planets to safeguard ourselves from this pollution, or after depletion of earth resources, how can we live? We should have some natural resources to sustain. So that's why space travel or colonization is important. Finally, colonizing other parts of solar system or other planets of solar system would prevent the whole human species from being exterminated by any one of a number of possible events. One of these possible events in an asteroid impact, for example, if any big sized astronaut, if it hits the earth's surface, what happens? There is a chance that human race may extinct. So to avoid this, if we are forming colonies on other planets, they can continue their life. Okay. Coming to the navigation. Throughout human history, we relied upon navigational skills. Whether you want to travel on land, sea or through air, we have to depend on certain instruments or certain knowledge. Over the centuries, while the vehicles and payloads have changed, there has always been a need to safely navigate to a new destination. So irrespective of the payloads or the vehicles technology, we always try to look for the safety while navigating or while traveling from one place to another place, or when you are traveling from a known location to unknown destination. Whether a person who is hiking in woods, or the person who is operating a boat, or a pilot who is flying an aircraft, there are fundamental components for successful navigation. If they want to reach their destination, there are fundamental components which they have to rely upon. For example, they should have a map, they should have a travel plan, a means for making observation. They should have some instruments for observing the far distance objects. A means for determining one's location, to identify their own position. They should know how to calculate their position. A method for selecting a new route when one has deviated from the travel plan. So all these are the fundamental components for successful navigation. Spacecraft navigation. We will now focus on the part that is spacecraft navigation. For spacecraft traveling in the solar system, the maps are referred to as ephemerides. They contain the time-varying locations of planets, moons, and other solar system bodies. As for aircraft navigation, we relied upon almanac, right? When you are using celestial navigation method, we are going to make use of almanac, which is a publication which includes information about celestial bodies and their orientation throughout the year. In the same way, we are going to depend on ephemerides. For spacecraft traveling in the solar system, the maps are referred to as ephemerides. They contain the time-varying locations of planets, moons, and other solar system bodies, such as comets or asteroids. There is a travel plan that is designed to deliver the spacecraft to its destination and still meet the constraints. Navigation observations in deep space can include spacecraft images of stars, solar system bodies, as well as changes in radio signals being sent to or received from the spacecraft. So, this navigational observations from the spacecraft will include images of stars, solar system bodies, as well as the images of RF signals. Calculating one's position, referred to as orbit determination, is performed by estimating the spacecraft trajectory based on collected measurements. So, as we said, the fundamental concept, one of the fundamental concept is determine one's location. So, to calculate one's position, we are going, which is referred as orbit determination. It can be performed by estimating spacecraft trajectory. Based on the measurements or based on the mission, we can design the trajectory, how and in which path the spacecraft has to travel to reach the destination. 8 for interplanetary navigation. Planetary ephemerides are developed at JPL and NASA in a continuous long-term activity. The team and its charter are unique. Orbits are refined using measurements from a variety of sources, such as rudder measurements from Earth, astrometric images, radio signals from spacecraft near the body of interest. Technical challenges in the calculation of ephemerides include orbiting long data arcs, adjusting dynamical models, determining constant frame times from celestial reference to solar system. See, aid for interplanetary navigation, we need some aid, we need some prerequisite for interplanetary travel. One prerequisite is planetary ephemerides. It is developed by JPL. Continuously they are going to upgrade this. And to prepare the ephemerides, planetary ephemerides, they are collecting information from variety of sources. We can rely upon radar measurements from the Earth. We can rely upon the astrometric images taken from the satellites. And we can rely upon the radio signals sent by the spacecraft from the spacecraft which is near the body of interest. If you want to design a trajectory to Mars or Venus, you have to consider the data which was already sent by the previous satellites. Then, coming to the technical challenges in preparation of ephemerides are, we have to concentrate on obtaining long data arcs or continuous data from time to time. Then adjusting dynamical models. Then third one is determining consistent frame times from celestial reference to solar system bodies. This is related to coordinate systems. Interplanetary GNSS. Many of the missions as exploration programs will require precise positioning, navigation and timing. We already discussed about aircraft GNSS or global navigation satellite systems to calculate one's position on the surface of the Earth or in the Earth atmosphere. In the same way, when you want to travel from one planet to another planet, we should have the information with respect to position, navigation and timing. Orbiting spacecraft, launch vehicles, surface activities with or without mobility, aeroboats and balloons would greatly benefit from a planet-wide, innovative and cost-effective position and navigation system. In addition to this, there is a strong real-time computation need due to the large distances involved in communication between Earth and other planets. See, the distance between one planet to another planet is very high. So we need communication systems and real-time computation of the data to get the accuracy or to achieve the accuracy. A precise and real-time global navigation satellite system would greatly enhance future interplanetary missions capabilities, as it would comprehensively fulfill the requirements of the activities mentioned above. In a similar way, navigation activities here on the Earth have been made easier because of the wide use of GPS and Galileo. Planetary activities would become much more sustainable, autonomous and efficient than before with the aid of such a dedicated system. If we have a GNSS for planetary navigation, we can rely upon that for sustainable and efficient data. However, although the launch and management of GPS satellites into Earth orbit is relatively commonplace, performing this for other planetary bodies is little difficult. The primary objective driving this activity is to perform preliminary design study along with a possible mission roadmap of global navigation satellite system into Martian or any other planet of solar system. At first, the needs of exploration missions are identified for a better understanding of the user requirement. You cannot simply build GNSS on Mars or Venus or for Jupiter. We have to study the user requirement for what the user or the country is exploring a planet. So based on user requirement, we have to design the mission. Follow-up work aims at defining the system architecture and designing the constellation itself. So initially, based on user requirement, we have to design the mission. After that, we have to design the system architecture. What should be the architecture to implement the mission? Then designing of these subsystems or the constellations. Then a mission analysis is performed, leading to launch scenarios of the whole constellation, spacecraft preliminary design, as well as suitable ground and user segment definition. It is acknowledged that such a system would greatly improve mission safety, reliability, which is highly desirable for sustainable and long-term space exploration program. So if you are performing all these steps, if you are implementing all these steps, then we can say that we can rely upon a particular system for its from the safety point of view as from the accuracy point of view. In this particular slide, the typical data types for interplanetary navigation system are listed. You can see this. There are different types of data such as Doppler, range, angles, DDOR and optical data. All these data has to be considered. From Doppler, typical mission phases for a particular data type. If you are considering Doppler, only data type used for Mars orbiting spacecraft and for other certain astronomical observations. If you are taking optical type of data, we can get approach value, proximity, satellite ephemeris updates from the help of optical data. Then mission design process elements. In mission design, we are going to consider or identify and gather general input requirements. That is the science and the basic flight system constraints. So we are discussing about, basically we are discussing about the mission design process or how you are going to design the mission. To design a mission, we need elements. What are those elements? First of all, identify the science behind the concept. Then identify the constraints of the system. What are the constraints to reach Mars? What are the constraints to reach Moon? What are the constraints to reach asteroid belt? Then, after defining these two, define and schedule and clarify responsibilities for sub-processes. Once you know what are the constraints, design the sub-processes based on the mission requirement, which includes mission planning or engineering process, trajectory design process, this is related to navigation, then navigation accuracy analysis. Iterate this with project management team. The next step is mission planning. First step is mission design, second step is mission planning. Take general inputs, requirements and constraints. Consider all these three parameters. Develop scenarios or concept of operations for mission events, such as development, launch readiness and flight operations. Each team has to be dedicated individually for these parameters. Then formulate baseline products and update the iterations. Trajectory. Initially you might have designed one trajectory, but after iterations you will identify, okay, there is some small error in the trajectory, you have to change the path. So implement that iterations, implement those values and finalize the design. Mission design and navigation components. Now in this particular slide we are comparing the task with respect to Earth as with respect to space navigation systems. First one, obtain a map. For example, if you want to navigate on Earth from one point to another point, if you want to travel from Delhi to Bangalore, you should have roadmap and digital map database. In the same way, if you want to travel from one planet to another planet, you have to develop planet ephemerides. Then develop a travel plan. Once you are having a roadmap, select trails to reach destination. Estimate arrival time. So if you want to travel from Delhi to Bangalore, you are going to calculate the time, right? What is the time required, or how much time it takes to reach from Delhi to Bangalore via flight or via train. In the same way, when you want to travel in space, select the orbits to reach the destination. It can be a planet or it can be an asteroid. Then calculate the time required. Third is take meaningful measurements, such as note time arrived at significant landmarks, note direction with a compass. And what are the measurements that has to be considered if you want to travel in space? Use radio signals or optical measurements to compute spacecraft propulsion and velocity, because velocity and position plays an important role if you are traveling from one planet to another planet. Calculate one's position. So calculate your position with respect to waypoint at a predicted time. In space, estimate the size, shape and orientation of the orbit. This is how you are going to calculate your position, whether you are at apogee or you are at perigee. Then select a new optimal route. Walk faster, slower, change your direction to reach the destination. In case of surface navigation on Earth. Same way, in space, you can change the orbit by using propulsion system, by increasing thrust or by changing the direction of thrust. We can select a optimal or new route. Observe this figure which talks about space navigation process. So if you want to launch a satellite, we are launching it from Earth. So Earth, layers of Earth atmosphere, then we'll be launching a satellite to study any planet or to study the star. Correct? We have to consider flight path optimization, flight path estimation. We should consider the models. It can be dynamic models or static models. Then consider the input from navigation systems. Consider the trajectory design tools to create the mission. Next is navigational accuracy analysis. Trade analysis, significant input and assumptions, significant products. In trade analysis, navigation performance as a function of certain constraints. Requirements on overall flight ground system needed to achieve certain navigation levels. Then, in significant input and assumptions, take the support from tracking systems, telemetry systems, navigation data types such as Doppler, Delta DOR, optical measurement, LIDAR measurements. In significant products, that is arrival statistics, recommendations for changing the inputs. Navigation objectives in different mission phases. Each phase of the navigating a spacecraft will consist different mission phases. For example, if you take orbiter, if the spacecraft is of orbiter type, you have to determine the trajectory on a continuous basis. Continuously have to monitor the satellite. And you have to maintain the desired orbit. For example, Chandrayaan, which is launched to study the surface of the moon. So what the scientist has to do, after launching, when you are placing Chandrayaan into the orbit, you have to continuously monitor the satellite or the Chandrayaan, and to ensure that it is in the desired orbit. What happens if it is deviated from the orbit? We may not get the accurate data which we want. And the other type of mission is like flyby or orbit insertion. You have to depend on deliver the spacecraft to desired location at a desired time. Here position and time plays an important role. Then predict encounter conditions for instrument pointing or sequencing, and obtain accurate post encounter solution. Okay, after placing the satellite into orbit, make sure that it is inserted at a particular point on the trajectory. This particular picture will show you different phases of mission from Earth to Moon. For example, you have to design ground segment, launcher and launch strategy when it comes to Earth. Then intermediate, you have to consider cruise and orbiter acquisition and deployment phases. Then after reaching Mars, you have to focus on communication and navigation. Even after placing an orbit in the Martian atmosphere, the ground stations on the Earth has to reach the data continuously or at the specified intervals of time from the satellites. The next is positioning system. When it comes to planetary system, we will be talking about deep space positioning systems, which is well known as DPS. It is a single device that provides a spacecraft position and velocity in interplanetary space. NASA Jet Propulsion Laboratory has developed a compact, low-power self-contained instrument that provides equivalent of GPS throughout the solar system without aid of artificially provided infrastructure. So GPS has developed an equipment with low power and self-contained instrument. It will provide accuracy, or it will provide the data similar to our GPS, but in the solar system or in the atmospheric of the solar system. The state-of-art external navigation instrument is also able to determine the position of spacecraft anywhere in the solar system, but it cannot provide the information relative to Earth, Sun or any other remote target body. JPL's unique capable deep space positioning system determine the position and target relative position of the spacecraft anywhere in the solar system using optical navigation, which makes it ideally suitable for any spacecraft requiring deep space navigation services. Even Mangalyaan mission was relied upon DPS. What are the benefits of deep space positioning system? DPS provides deep space navigation and target relative navigation without aid of artificially provided infrastructure. Without using any external infrastructure, we can make use of DPS. No need to set up a new deep space network to communicate between the Martian satellite, that is Mangalyaan, and the ground station. Placement of wide and narrow angle cameras guarantees co-bore sighting throughout the celiostat. Here we came across a new word, that is celiostat. What is celiostat? It is an instrument with a rotating mirror that continuously reflects the light from the same area of the sky, which can be used for monitoring the path of a celestial object. Celiostat relies the spacecraft pointing equipment with respect to navigation imaging and radiometric link closure. So you can depend on celiostat, which is the part of DPS. Applications of DPS. It can be used for deep space navigation instruments. So instead of directly sending information from Mangalyaan to Earth or to India, we can, the satellite Mangalyaan can send information, or the corrections can be sent from DPS to Mangalyaan. So it is like uplink and downlink. Then asteroid reconnaissance and mineral prospecting missions, we can rely upon DPS. Human mission to Mars can make use of DPS to identify its position while orbiting the Mars. Okay. So this is about interplanetary navigation systems and interplanetary positioning systems. Now we'll just have an idea about Mars orbiter mission, MOM, or it is called as Mangalyaan. It was designed and launched by ISRO on November 5th, 2013. One of the main objectives of the first Indian mission to Mars is to develop the technology required for design, planning, management and operations of an interplanetary mission. This was the first interplanetary mission which belongs to India. Following are the major objectives of the mission in terms of technology and science. The technological objectives includes design and realization of Mars orbiter with a capability to survive and perform earthbound maneuvers, cruise phase of 300 days, Mars orbit insertion, capture and non-orbit phase around the Mars. Second objective is deep space communication, navigation, mission planning and management. Third objective is incorporate autonomous feature to handle contingency situations. To demonstrate these objectives, the Mangalyaan was designed. And the scientific objective behind Mangalyaan is exploration of Mars surface features, morphology, mineralogy. What are the minerals that are present or existing in Mars? And Martian atmosphere by indigenous scientific instruments. With the help of indigenously developed scientific instruments, we want to study the surface features of Mars. This particular picture shows about the Mars insertion or the trajectory profile. You can see the Mars at departure. Okay, this is Earth. So how Earth orbit. Then you will be having an intermediate orbit. After passing through this intermediate orbit, it will be inserted into a orbit around the planet Mars. This is the trajectory. I think from this picture it is clearly understood. Correct? You are launching from Earth. So you will be having Earth parking orbit. Directly you cannot send the satellite to Mars in a straight path because the revolution period of Earth and Mars are different. So Earth, you are going to design Earth parking orbits. Then you are going to transfer Mars transfer trajectory. You are going to transfer the orbit. Finally, you are going to insert the satellite in the Mars orbit. So can you see the picture in the right corner? DSN, that is Deep Space Network. But okay, we cannot see after launch, we cannot see the satellite through naked eyes. But how you will get to know whether it is going in the correct path or whether it is deviated from its path? By using DSN. The three stages of Mangalyaan include geocentric phase, heliocentric phase and Martian phase. Geocentric phase, it includes departure hyperbolic trajectory and escape the sphere of influence of the Earth. Then heliocentric, the spacecraft leaves in a direction tangential to the Earth, orbit and encountered Mars tangentially to its orbit. This is the intermediate phase. Then third phase is Martian phase. The spacecraft is scheduled to arrive at Mars sphere of influence from the hyperbolic trajectory. Next is navigation part of Mangalyaan. It includes telemetry, command and tracking, which is called as TTC. The Deep Space, the Indian Space Research Organization Telemetry Tracking and Command Network, that is TTC network, performed navigation and tracking operations for the launch with ground stations at Sriharikota, Port Blair, Brunch and Bake in Indonesia. And after the spacecraft apogee become more than 1 lakh kilometers, two large 8 meter and 32 meter diameter antennas of Indian Deep Space Network started to be utilized for sending commands to the satellite or for the telemetric purpose. The 18 meter diameter dish antenna will be used for communication with craft till April 2014, almost for 6 months, after which the larger 32 meter antenna will be used. They also used NASA's Deep Space Network is providing position data through 3 stations located in Canberra, Madrid and Goldstone on the US West Coast during non-visible period of ISRO's network. So because of the rotation of the Earth, only for few or only for certain duration, Mangalyaan can be visible or tracked from India. But for the remaining duration, we depended on NASA's Deep Space Network. Then the South African National Space Agency, that is SANSA, ground station also provided satellite tracking, telemetry and command services for Mangalyaan mission. We are thankful for that. Additional monitoring is provided by technicians on board 2 leased ships from Shipping Corporation of India, which are placed at Nalanda, which are called as SCI Nalanda and SCI Yamuna, which are currently positioned in South Pacific near Fiji. So we are made use of these two ships. Then tracking was done by Indian's Deep Space Network will perform navigation and tracking operations of the mission, and NASA's Deep Space Network will provide support services during non-visible period of Indian Deep Space Network. The signals from the orbiter takes as much as 20 minutes to reach Earth. Also, some of the ships positioned in the South Pacific Ocean will help in tracking and coordinating the spacecraft. So this completes the session about interplanetary navigation systems. Thank you. I like to thank Mr. Moz Hussain and his team for giving me an opportunity to speak on advances in navigation systems. I like to thank their technical team as well. And finally, it's the audience like you that make presentations awesome. I remain most grateful for the rapt attention with which you sat throughout all the sessions. I'm confident that you have learned something from it. Thank you very much.